So with the previous discussions, we are now in position to define the product measure. So let us define the map mu cross nu on the product sigma algebra to the interval 0 to infinity as follows. So for a set A in the product sigma algebra, let us define this to be the integral of the composition of the measure nu with respect to the section y. So we write the composition in this way, and let us emphasize that this is a function of x. So here we put the variable of integration. And the previous theorem tells us that we can instead use the measure mu, but integrate this over y of the section on x. And again, we emphasize the variable y for the integration. If I have an ordered pair, the Cartesian product of x and y, and an element A in the Borel or in the product sigma algebra, then the value of the characteristic function at the point xy. So this is one if and only if x is in the section on y of A at the point x, and if this is the point y is also in this section. And you can interchange the section and the argument, and you have this. Therefore, the integral of the characteristic function integrating with respect to nu and then with respect to mu, and using the first equation, this would be the characteristic function of the section on y evaluated at x at the point y, and solving the inner integral, this is the same as nu of sy, since this is a simple function, d mu x. Now, applying this equality here, we get that this is also the same as the following. So mu sx y d nu y. The measure can be written as the integral of this step or simple function sx to a, and you get the second characteristic function. So take note by definition that these two are equal to the product measure of A. So to summarize, and then ignoring the variables of integration, we can alternatively define mu star nu of A to be the integral over x, the integral over y of the characteristic function. From here, you can interchange the order of integration. And based on this discussion, we have the following theorem. So let us consider two sigma finite measure spaces. Then the function that we defined above is the unique measure defined on the product sigma algebra, such that the product measure of the Cartesian product is the product of the measures of the corresponding sets. This is true for any E cross F in sigma cross T. And also, this triple is a sigma finite measure space. So for the proof, if I take an E cross F in sigma cross T, then according to this formula, so let us use one of them. This is the integral over x of the integral over y of the characteristic function, the Cartesian product. So this characteristic function is 1 precisely when the x component is in E and the y component is in F. Here, this product of two functions evaluated at an ordered pair is the product of these characteristic functions evaluated at the corresponding components. So here you can, of course, show that this is the characteristic function of E times nu of F. Since this is a simple function. And this is the same as mu of E, nu of F. And this is establishes this property. And now the rest is apply the fact that this one generates the product sigma algebra and the uniqueness theorem for sigma finite measures. And you can also easily show that applying the sigma finiteness of these two measures, this product sigma algebra or product measure space is also sigma finite. So this is what we call the product measure space. And this is the way we construct it. And thanks to this theorem, we can now state the following theorem, namely the Fubini-Tonelli theorem, which aims to write, let's say, a double integral by this we mean precisely integral over a product space can be written as an iterated integral. So we iterate. We integrate with respect to one space and then integrate to another space. So let us state this more precisely. Again, we have two sigma finite measure spaces. And a function f from x cross y into k. And let us define the map Ix. Let us suppose that this is measurable. Okay. Now define this Ix f. So this is a function from x to k, and similarly Iy. I here refers to an integral. Okay. As follows. So Ix of f, this is a function. So it takes an input in capital X. So we take the trace function, okay, d nu y. So this is for x in capital X. And similarly for I, y. So this is an integral over x of this section. So for the first part, if let's say f is a non-negative measurable function, okay, then these integrals, okay, are also non-negative. So this must be in m plus x sigma, and similarly for Iy, m plus yt. And furthermore, the integral over the product space of f with respect to the product measure, this is the same as the following iterated integral. So we can integrate first with respect to nu, followed by mu, and you get the same when you interchange the order of integration. And let us say that this is equality star. Now, for the second case, so if let's say f is Lebesgue integrable, okay, where again k here is either the set of non-extended real or the real numbers or the complex numbers. So if f is integrable, f is integrable if and only if these functions ix replaced by the absolute value is integrable, and similarly for y. Now, if this is the case, the above identity also holds. So this is the Fubini-Tonelli theorem, and I will emphasize here the main result is that we can write the integral over the product space as an iterated integral. So you integrate with respect to one measure and then followed by the other. And moreover, this means that the order of integration is does not matter. I will not give the precise proof, but allow me to present the idea of the proof. And this is via what I call the Lebesgue, Du Bois-Reymond strategy. And the strategy is as follows. So as a first step, you take the case of characteristic functions of sets in the product sigma algebra. Well, this follows from the above discussion. Why? Namely, this one. And I take note that this can be written as the integral of the characteristic function of A. So let us emphasize here. So this can be written as the integral of A, or the characteristic function of A with respect to the product measure by the definition. Okay, so here you can write the double integral as an iterated integral, and the order is immaterial. So that's the first step. The second one is for a simple let's say for simple functions, non-negative simple functions, let's say. And here you apply the first step and linearity of the Lebesgue integral. Once you know this, okay, for non-negative measurable functions. So in other words, you are in this class, you take an increasing sequence of simple functions in S plus that converge to the non-negative measurable function. And here we know that such a sequence exists by our previous discussions, and apply the monotone convergence theorem. Now the next step, what if we have the real valued case? So real valued integrable functions. So that is in L1 X. Okay, let's say real valued integrable functions. So for this, you separate the positive and negative parts and apply the previous step. And finally, for complex valued functions, complex valued integrable functions, as usual, you separate the real and imaginary parts and apply the previous step. So basically, this strategy follows from our development of the Lebesgue integral. So from simple functions to non-negative measurable functions to real valued functions, and then finally for complex valued integrable functions. So the crucial step here is step 0, where we need to verify the theorem in the case of characteristic functions defined on sets in the product sigma algebra. But the way we constructed the product measure guarantees that this is valid. Okay, so I will not go into the details of these steps. Nevertheless, these are presented in the course notes and you can read them in detail there. Let us now extend this to several measure spaces. And of course, let us start with 3 measure space first. So let xj, sigma j, mu j be a sigma finite measure space for j from 1 to 3. Then we have the following property. So the product measure is associative. I would like to point out here that the product sigma algebra is associative, okay, as we have discussed previously. Okay. In particular, we would like to note that this notation is unambiguous. By this, I mean that, of course, you can first consider this product measure, or you can consider this, but according to the previous theorem, they are the same. So the order or the grouping is immaterial in this case. Again, I will not give the full details, but I'll just present the idea of the proof. So here you want to show that the two product measures are equal on a generator, namely this one. And then apply the uniqueness theorem again for sigma finite measures. So that's the proof idea. And of course, equality here follows immediately from the property, or follows from this theorem stated a while ago. And you can put the details there. So we can now proceed inductively, so that n greater or equal to 2, and of course this is an integer, and for each let's say j from 1 to n, consider a sigma finite measure space. And now we define this product measure. So mu sub j, so this is mu1 cross mu2 if n is equal to 2, and for n greater than 2, you take the product measure up to the first n minus 1, and then take the product measure with respect to the last. So this is our definition. In the event that these measure spaces are all the same, let's say we can remove the indices for all j, and then we define x to the n. So this is the usual notation for the Cartesian product, and we adapt this in the case of the sigma algebra. And likewise with the measure. If I have a generator, okay, now going back to the general case, if I have a generator E sub j of the sigma algebra sigma sub j, then we know that, okay, this is the same as the sigma algebra generated by the Cartesian product of the generators. And we have established this last time. Now, applying the associativity of the product sigma algebra, so given an integer m between 1 to n, it can be 1, but it cannot be n. We have the associative property so here you take first the product sigma algebra up to the m sets, and then the product sigma algebra of the remaining sets. This is the same as the product sigma algebra of the whole collection of sets. And this is also valid in the case of measures. And this is, you can prove this by induction, since we already know this in the case of 3 sets. Okay. So to summarize these discussions, let us state the following theorem. So consider a finite collection of sigma finite measure spaces. So let's say for j from 1 to up to n, with n an integer greater or equal to 2. And then taking this triple, take the Cartesian product of the sets, take the product sigma algebra, then take the product measures. Okay, this is sigma finite measure space. In addition, well, you can show that if I take the measure of the Cartesian product of, let's say, E sub j, j from 1 to n, where E sub j is an element of sigma sub j, j from 1 to n. This is the same as the product of the measures. And this is the unique measure wherein we have this property. So the proof is via induction, and we do not provide it here. Just a quick example. In the context of the Lebesgue measure in Rn, or Lebesgue-Borel measure, in Rn. So first, the Borel sigma algebra on Rn. We know that this is the product of the Borel sigma algebras of R. And the Lebesgue-Borel measure lambda n is also the Cartesian product of the one-dimensional Lebesgue measure. And you can prove this basically by the uniqueness theorem. So to close this lecture, let me present to you the generalization of the Fubini-Tonelli theorem in the case of finite product measure space. So let us consider, let's say, a positive integer greater or equal to 2. N equal to 2 will be your usual Fubini-Tonelli theorem. And a finite collection of sigma finite measure spaces. Since we want to state the fact that the integral over the product space can be written as an iterated integral and the order is immaterial. So we need a way on how to describe the reordering. And this is done precisely by, let's say, a partition. So pi be a partition, or I should say permutation. So this is an injective and an onto map. So if f is either first consider a function f on the product to the field k, either the set of real numbers or the set of complex numbers. If f is either non-negative, must be measurable at first. If f is non-negative or it is integrable, then the product or the integral over the product space of f with respect to the product measure is the same as the following iterated integrals. So first you take the image with respect to the permutation pi of 1 up to the last image of the permutation. And you have this iterated integral. And this is the same. So this simply means that order of integration does not matter. Okay, so one can, of course, establish this via induction and the Fubini-Tuneli theorem for two measure spaces. And that's it for this section. In the next series of lectures, we will discuss integration through image measures and also the change of variables formula. See you then.